Hello and welcome. I'm Shadow of Shadow Gaming, bringing you Programming with Shadow, episode number 68. In today's lesson, we are going to begin looking at an AVL tree. So in the past lessons, we've looked at a binary search tree, and we've seen that in the worst case, you can get a linked list, so a list that's all one-sided or very heavily favored to one side. So the idea from there becomes you want to balance the tree, get it to look more like this rather than this. And that's what AVL was one of the first trees that did that. Meant to look up AVL tree. It's named after two people. I think they were in the Soviet Union in maybe the 50s or 60s. Meant to look it up, but I did not do that. But it's their initials, I believe, or a part of their names or something. Somehow it gets its name related to that. So what we're going to do today, though, is try to look at it and maybe even try to implement a little bit there. So we will probably just use these actually. Let's make it a little more usable though. Oops. Yeah, there's probably a quicker way to do this, but this is how I'm doing it. We're seeing it's looking like a linked list for sure with this, though. That's the purpose. Okay, so let's begin. So, as I said, the idea of an AVL tree is it's balancing. So, they basically, what the tree is, all the properties of the trees we've looked at already sort of still hold true. AVL is looking at keeping it balanced so it doesn't look like this. So there we have the concept of height we talked about, and in this case the height is it's O of n. It keeps growing if we kept adding the numbers. The search time because of that also keeps growing, so this is just a linked list, so we'd have to search through everything to get there. So the idea there is we wanted to keep the tree shorter, and that helps us keep it more balanced. So AVL tree enforces this by keeping heights, or the height difference between the right side and left side, at less than 1. It might be less than or equal to 1. It's got to be less than or equal to 1, yes. And it does that through the introduction of something that it's called a balance factor, which is equal to the height of the left minus the height of the right, something like that. So basically, if this is equal to -1, 0, or +1, the tree is fine. Anything else, it's unbalanced and you need to do some work to it. So let's see. So height, or let's see. I was going to try to see the height, but I didn't write down it. I haven't wrote it down yet. Yeah, I actually don't have it. So basically you keep track of each node's height though. So you start maybe 0, then 1, 2, 3, 4, 5, 6, 7. So there you would have a height. This one's there's a height of 7 here. Maybe something like that. Here you would have 0, level 1, level 2, 1 and 2. There's only a 1 size difference, so maybe that's still balanced. And it probably should be. So that's the goal though, is to keep it balanced via keeping track of this. So what we're going to do today is we're going to do a program similar to this. In fact, I'm probably going to copy this and we will do an AVL tree visualizer. In fact, we probably can just do it in here actually. So I haven't done a lot of this yet, but in Visual Studio, you can right click a solution and you can add a new project. That lets you have two similar programs, so I can have two console apps. And we'll see there's a little bit more we have to do, but in general, that's just going to work. So we will call this AVL Tree Visualizer. There we go. So I'm just going to grab this, everything inside here. I'm just going to slap it in here, and we'll make some changes as we need to. Tree printer. So that was our little helper here. I think I'm going to want that in multiple places. So what I'm going to do is I'm going to add a third project here. We're just going to call this, we're going to pick class library this time instead of console app. We're going to say, tree visualizer logic, maybe something like that. So this, I'm just using it as well, this is going to be, it's not going to be a great example of this, but it's going to be a little it's basically, I'm going to copy this and make it class 1. And what I'm thinking is, instead of this, let's have a, I'm trying to think what else I'll need. Let's do it like this. Let's let me rename this. Right now it's named class 1. Let's rename it to tree printer. So what it's fussing here is it needs to know what BST node is. Let's do it like this. Let's do public class tree node. Let's do it like this. And it'll have it'll be basically the BST node. We're going to add one more property to it. We're going to add public int height. Tree node. And height is optional. I think we'll be able to do this correctly. So now this becomes tree node. And there we go. Now BST node, tree node. We'll make it inherit, though it can't find it by default. So the type cannot be found. Are you missing a directive or an assembly reference? So this add reference here is what we'll need to do. And I'm going to click this one here just to show you can do it from here. That fixed it, and now it can know what it's looking for. And it's already got all those fields, so we don't actually need those. So that's one way to do it. The other way to do it is come in here, right click, and you can go to add. You get the add project reference. So this says this one needs to rely on my tree visualizer logic. That's the library. And there we've hooked them all together. So if we open up the Solution Explorer, or not the Solution Explorer, the project itself, let's see if I can find edit project file here. You can see that what it adds to your CS proj is it adds an actual reference. It says include this logic as well. So that's what's actually happening there. So there we've got us a tree printer that's not this one. And this one can now go away. So this one. Now we need to come over here to our program and we need to get it working again. Yeah, there we go. So control dot using the tree visualizer logic. There we go. All right, so we've got that hooked back together. I believe that has everything fixed for the... Oh, no, we do need to fix this class, I guess. Oh, basically, what this is coming to is I don't actually need this. Let's just delete this. There's no extension we need here, so I guess that makes sense. In fact, I guess we don't need height. Yeah, let's get rid of that. I guess we can use the tree node. And now at that point, we don't need the BST node. And at that point, then I just need to make this. All right, Alt Shift semicolons, what I did to select all of them. Now I just type tree node. I know what I called it. There, and add to using. So now we should be rebuilding now, I believe. Unless we used it in here. We did use it in here, didn't we? That's the new one. Comment out. Comment out. Rebuild. And there we go. Now it built. And we should have restored our logic from last time. We can run it real quick just to check. Insert 5, 7, 2, 9, 8. See, there we go. We made us one that's not balanced now. Oh, I guess that one's still... Nah, that's not balanced. Yeah, one that's not balanced. So the AVL tree would have to do something else with that. So we'll go ahead and say we've at least got it working. So hopefully we should be good there. So what we can now do is we can start adjusting this program. This one. So what we're going to add here is add a new class for an AVL tree. Okay. Up here, Control U, Control K, Control U. We'll have this AVL tree. AVL tree visualizer. Here we'll rename this Control RR AVL tree. Copy all the inner part here for the moment. Tree node. Let's pull this up to printer here. There, and we can make this its own file. Control dot, move type to new file. Now we've got a print and order method, so now we need to go back and fix our BST visualizer because we just broke it. Now we broke it. Tree printer. There we go. Now we fixed it again. Over here we can just say that same thing. Okay, and that added our using statement. Okay, so we'll come back to delete in a minute. We're going to start. Search will be about the same. We won't really change search. So the one that will change is insert, however. And let's do this. So public class AVL tree node. So this one's a more complex tree node. So let's do this. So it has that method, but it also has public int height. Something like that. So now, instead of tree nodes here, we're going to use this instead. So I'm going to select this here, Alt Shift dot dot dot. I think there's one more usage, two more usages. And I'm going to say AVL tree node, like that. Egg. You can tell I did, this was I changed my implementation here. Let's do this. Since it doesn't like that. Didn't it like that? Wait a minute. I guess I shouldn't. I guess what I'm trying to do here is not going to be what I want, I guess. So let's do it like this. And here we'll just get rid of that. Not exactly what I wanted to do, but I guess this will work. Did I not just deal with that? Oh, tree node. There. Okay. And we may try to come back and refactor that, because what I'd like here is just to be able to use this and extend it. And I think what I actually want is an interface instead of a class, is a class rather. I think that's actually what I was trying to do there and just didn't do it right. But yeah, we'll use this instead. So AVL tree node. So insert. So let's get our tree back here. Go ahead and close this. What is this complaining about? Yeah, that makes sense. F12. Yeah, that should technically actually still work, but yeah, it's up. Let's see. Let's do a slightly different print, I guess. We'll do let's do this. Let's grab my node here, cut, paste it in here. We'll make it a new CS proj here, and now let's do our own public static void print. This one will take an AVL tree root, and we'll have an int indent equals 0 just like before. This one, let's do a little bit, it'll be very similar, so we'll copy everything for the moment. Let's see if we don't need to make a change. I think I need to make a change. And again, this looks like a structure that an interface is what I'm actually after instead of what I was trying to do. So I think that makes sense. So let's see. Space indent. Let's worry about, so we're going to have some more properties here that we don't have in this situation. So let's do this plus root dot value. I'm trying to think how best to present this. We'll do it like this. All right. Yeah, let's do it like this. Get balance. Passing in root. Yeah, let's have a static helper here. Static int get balance. AVL tree node. So get balance here's that's what I mentioned before. So this will be the left minus the height of the left minus the height of the right. So what we could do there is int left height equals node dot left if it exists dot height, or it becomes 0. Int right height equals node dot right if it exists dot height, or 0. Then return left height minus right height. There we go. There's just a little helper there. So there should be a printer now, so we should still have one failing. Yeah, same thing. Same thing. This should be an interface rather than a class. So we'll just duplicate it for now. There we go. So yeah, this is looking very much like this should be an interface, and then these two slightly different things. So maybe we have a tree printer that has this one in it, and then you have concrete ones for, maybe this is virtual then, and you have a AVL tree printer, maybe something like that. Okay, let's get back over here though. So let's begin with actually building out the AVL tree. So its operations are balancing this. So the idea is you rotate. So let's see, I think this one's a little, it's a little heavier on the right side, but we'll see there's 4 types of rotations. So what we could do here, let me copy all of these. Let's make another one. So what we could do here is perform a rotate. So what I believe we'll want to do is make this one come up. Let's see if this works. So 7 come up. So then we'll have 7, 6, that causes 11. Oops. Causes 11 to go down. Then we got 20. And over here, we have 3. And now it's balanced. So what that does is you rotated 11 up, or 7 up to the root, and everything else moved around. And we're going to implement that here. So the balancing for a AVL tree is done on insert and deletion. Deletion's more complicated. I think we won't actually get to it today. I think it'll be next lesson, but we'll see if we have time. Let's begin here. So the first thing we want is a helper method. So let's add static int height AVL tree node. If it exists, dot height, else the height is 0. Now we'll have a static int get balance AVL tree node. All right, so this is we'll do our guard here. Node is null. Return 0. Copilot's there bothering me again. Return height node dot left minus the height of node dot right. I really think Copilot's getting worse instead of better. Right, let's do one more. We'll have a static int. Let's do void update height AVL tree node. So this one, yeah, I really think it's getting worse. So this one, what we're going to use this for is to go through and see which height's the larger one and increment it. So we'll have node dot height gets 1. Sorry about that. Sneezed there for a second. So it gets 1 plus, let's do a math dot max of height node dot left height of node dot right. All right, I think that's what I want. So let's do this. Let's make this over so we can see it. So that gives us the height of a specific node, and we'll see how we use that here in insert. So now let's write the major functionality. So rotate right. So we'll do AVL tree node rotate right. AVL tree node. No, I want to say node here. What's going to happen is there's going to be a second one, however. Let's do like I'll do it like this. So the reason I'm picking this is what some of the definitions you might read, like on say Wikipedia, or if you have some of the books, this might be how they actually do it. So let's do that. Let's do it like that. So now we'll have a AVL tree node x gets y dot left AVL tree node T2, so temporary node 2 equals x dot right. So what that does is we pass in maybe 11 here. So rotate right's the one we did. So we'll pass in 11. So x becomes 6. T2 becomes 7. What we're going to do is we're going to do some swapping. So x dot right equals y. So basically set 11 to 7. Y dot left equals T2. 7's left became this one. Wait, no. Wait a minute. Here, let's do it like this. Y X T2 so this becomes 11. Seven becomes 11's left becomes 7. I think I'm actually interpreting this wrong visually, actually. I don't think I'm visualizing this correctly, actually. Let's keep it up, but I may need to check this, actually, before we go too much farther. Update height, so that, and return X. So here, right may be null, and that's okay. Yeah, that's okay, because if it's null, we just pass the null on. Update height should be able to take a null value then. Is that a problem? Height with null? It does. Okay, yeah, not a problem. So that means this can be null though. So that means we need to do, go ahead and do rotate right and rotate left. This one will use X. So this will be very similar. AVL tree node Y equals X dot right. AVL tree node T2 equals Y dot left. So Y dot left equals X. X dot right equals T2. Update height of X. Update height of Y. Return Y. Wait a minute. Did this one do what I want it to do? And we need to pass through our whatever these are. Our null coalescing operators. So let's see if this one is this maybe what I've got wrong. So this one's X in this case. X is right, which is 20. Becomes Y. 1, 2, 3. Yeah, I still don't think that's right. And then T2 becomes Y's left. There's no left. I think I'm trying to visualize this wrong. I may need to actually look that up for next lesson. But I think we can keep going and actually see it in operation here. So let's do insert. So let's take those values. So first things first, if node is null, so if the node's null, it's easy. So we'll just return a new AVL tree node. Value equals value and height equals 1. And we're done. So that one's easy. So now we need the other two cases. So first one, if value is less than node.value, node.left equals insert node.left value. So add it to the left side. Else if value is greater than node.value, node.right equals insert node.right value. else return node. So those are the three cases. So now there's more work we need to do though, because that looks very similar to our BST's insert. The three cases here. So that's BST's insert. So now we want to balance it. So let's begin. Update height on the node. So go ahead and update the height. So set whatever our starting position correctly is. So int balance equals get balance of node. To figure out what its value is, what its balance factor is. Let's call it balance factor since that's what I used over there. Let's do it like this. Get balance factor. We'll do it like that and we'll leave balance separate here. All right, so now, we'll say a left LL rotation. So if balance is greater than 1 and value is less than node dot left dot value, return rotate right node. What? Oh, these need to be static. I was like, what's it saying? Yeah, now it's saying, warning us it can be null. Should it be able to be null? Wait a minute. I'm not convinced that should actually be valid. I'm a little suspicious on them. I may need to check those just a little more. So let's go ahead and implement, but I'm not sure on that. Our rotation, if balance is less than -1 and value of greater than node dot left, node dot right dot value, return rotate left node. Yeah, I think I've got my nullability messed up here too. So left, right, LR, rotation. If balance is greater than 1 and node dot left dot value greater than node dot left dot value. This is not this condition. It's close, but the signs are flipped. Return no node dot left equals rotate right node dot left, and then return rotate right. The last condition is the inverse, so right left RL rotation. If balance is less than -1 and value is greater than node dot right dot value, node dot right equals rotate right node dot right This one shouldn't be that, right? Wait a minute. I think I've done a wrong in my pre-work. I think this should be left. I think that's wrong in my example I'm following. I coded it wrong last night, I guess. Let's mark that here to do, make sure this is the right direction. All right, so there we go. That should be us an insert. So let's see what happens. So right now it's targeting the BST visualizer. I come over here. I come here and click this drop down. I have the option here of AVL Tree Visualizer instead. Let's run it and let's see what happens. Delete's going to be messed up. Note that we have not implemented delete. In fact, we should probably set it to not implemented. Here, let's make their tree look like this. So 1, insert 11. 1, insert 20. 1, insert 6. So tree's still good. 1, insert 3. 1, insert 7. Right. So the tree looks fine. So that one's balanced. So, okay. So now, let's add something on the left side. Let's add a 2. So insert a 2. So what we think is going to happen on their other one, it would just add here. So on a binary search tree, to add another one below the 3 here. What we think is going to happen instead, it's going to rotate, and one of these is going to end up as the root. Let's see. I'm mixing up my visualizer. 6. So it went from this tree here, where 6 was a subtree, to 6 is now the root of everything. And look, now the balance is still, rather than adding a new node and having it a 4th layer here, now everything's still on the second or 3rd layer, sorry. Everything's still on the 2nd layer. Let's add something else over here. Let's add a 1. Now, there was a rotation that happened here. So the 2 rotated up and the 3 rotated down, which seems all right. Happens if we add a 0. The 0 is going to try to go over here. And I think that'll be fine. Yeah. Let's add a... I've almost filled out this side. I picked the wrong side to try to do this on. Let's add a 5 and then a 4. Again, not a lot changed there. It just added it because it's still relatively balanced. And there it added the 4, but then it had to do a little bit of rotation. It rotated the 3 down and the 4 up. So that's sort of what's happening, though, is those kinds of rotations. You can see here all the balances that the leaves are 0. Going up, it just goes up to 1. There's only a 1 here at the root. Any other ones? Yeah, this one's got a 1. So it's saying there's a 1 difference between the sub-children. Let's do this. Let's add a, pretty much completely loaded this side. Let's add a -1. Let's add a -3. So now what I'm expecting is to see that this 6 is no longer the root, and instead it's going to be honestly don't know which one it's going to be. It's going to be one of these 3, I think, but I don't know which one. Let's see. Nope, it stayed a 6. What happened? Let's compare those two. We inserted -3, 0 rotated up, 1 rotated up. Okay, yeah, that makes sense actually. Yeah, it inserted here and kept this side balanced because this one's still fine. Now let's do the -1 though. There we go. There we go. That's what I was trying to get to. So when we inserted the -1 there, now suddenly it was trying to put the -1 here on this one's one, and then suddenly now everything was out of sync. So now it had to rebalance. So 3 rotated up, 0 rotated up to the root, or not the root, but the subtree root, and then 2 upgraded to the tree root. So yeah, I did. So yeah, this one didn't even need rebalance. So this one's completely wrong. Okay, but yeah, there's us an AVL tree insert. So delete messes all that up though, because right now we've still got delete as the other one. So if we try to delete, maybe let's delete 4. Yeah, let's delete 4. It worked, but I think that balance is still alright actually. Yeah, I picked a leaf node, so never mind. That was that a leaf? No, that's not a leaf. Oh, and it picked 5, which was a leaf node. Okay, yeah. So yeah, so I'm not exactly sure that's what we want to do. That should break it if you keep doing it and don't rebalance. Let's delete 5. Oh, that was, yeah, wrong one. Delete 5, promote left. Delete 6. I'm trying to get the balances off. Let's just delete 7. Delete 7. Not doing too well here. I think it's just completely lost at this point. There we go. There we finally broke the property. So now balance is 2. So what an AVL tree should try to do there instead of that is it should try to balance in that case. So in this case, we didn't balance. So that'll be the next thing. So let's go over here. Let's exit. So we'll do, instead of this, throw new not implemented exception. This will be done in the next episode. We'll redo it like that. So we're going to stop there. I'll try to do a little bit of better on the example side of things. I'm not happy with this one because what am I thinking? I feel like that needed to be balanced, but yeah, I guess that is balanced. So what it's saying is if I added maybe a 7's a terrible one to do it though. Let's do it here. If we added maybe maybe a 4 here, now it's not balanced, and that's when you would want to do some rotations to fix it. So what I'll plan for next time, I'll check these because I feel like I've got my example does not have these set, so I thought I didn't need to deal with null here. I got null wrong somewhere, and I'm going to need to figure out where. There. I wonder if update height even needed to be null. Let's see, what does anything break if we don't make it null? Yeah, X may be null there. Height. Yeah, height can be null. Yeah, I think that's fine. So I guess what we're saying is node here can't be null. So maybe instead of this, maybe what we want to do is if node is null, throw new argument null exception name of node. Yeah, I think that maybe that's what we want. Yeah, we can simplify that with the new syntax. Maybe that's what we want. So now we say update height. If update height is null, we throw. And then at that point, we would want to actually check and see why if these should be nullable or not. I guess they should because it's available. Yeah, I'll have to think on that a little bit, but yeah. There's just a visualizer, and it gives us a good start for next time. So we'll call it there. So in today's lesson, we've looked at inserting in an AVL tree. And we've also messed up some of our printing stuff. So maybe the next time we'll also look into cleaning that up a little bit. So I believe I should just pull these up to interface and be fine with. I'm not have to duplicate as much logic here, but we'll see. Yeah, we'll stop there. So next time we'll continue on with AVL trees. So thanks for watching and have a wonderful rest of your day.